All right, so for this, we're introducing the last type of distribution that we need to be familiar with in this course, which is a Poisson distribution, which is quite similar to a binomial distribution in many ways, except the only parameter we need is usually called m, which is the mean value, which is based on historical data. Usually it's a type of rate, quite often over time, but it's a rate of some sort. And that's the only value we need. The main difference compared to a binomial distribution is instead of looking at a number of trials, which is discrete, we look at a period of time or a period of distance, something that's continuous. But we still need to have events that are independent of one another, and the events must still occur singly, which means we can count them. The actual events are discrete, but they occur over a continuous time frame. So, for example, we have this water pipe that has an average of 3 leaks every 5 kilometers, distributed independently of each other. And an inspector examines a 5-kilometer section of the pipe. So what's the probability that he finds exactly 2 leaks? So for this, notice we want to find the probability of 2 leaks over a 5-kilometer section. 5 kilometers, that's not a number of trials. That's a continuous measurement of distance. But it has, we still know the probability we don't know the probability, we know the average rate of leaks, which is 3 per 5 kilometers. And so in this case, our mean, or our m, is just 3. And that's the only parameter we need. And so we can say here that I want to find, or maybe I'll start a bit more formally. I'll say we have a random variable x that is distributed with a Poisson distribution. And so I should have a little O there, and in which the mean is 3, and that's all we need. So that's a formal way of showing the distribution. And in this case, I can use my GDC, in which I have my m, or your GDC will probably use mu, and I'll have x, the number of leaks in this case being exactly 2. For example, on the TI-84, we want to use the Poisson probability distribution function, in which we have, again, the average of 3, x is 2, and it should almost right away just give us a value of approximately 0.224 or 22.4% probability. And that's the probability of exactly 2 leaks. If we want at least or less than or greater than, then we want to use the cumulative distribution function. We got to be a little bit careful here. So if we want to find the probability of at least 2 leaks, then I can write it as finding the probability. In fact, if we go back to the previous question, I can say I'm asking for what's the probability of x equaling 2? That's what we figured out in the last question. In this question, I'm trying to figure out what's the probability that x is greater than or equal to 2, at least 2. Now, most calculators don't have the ability to calculate this directly. They can only show where something is less than. So, well, that's not a big deal. I can say this is the same as 1 minus the probability of x being less than 2. These are correct. However, for example, in the T84, if we use the Poisson cumulative distribution function, it is going to be showing us where it's less than or equal to. I don't want that less than or equal to. I want just less than 2. And keep in mind, 2 is the number of leaks. We have to have a whole number of leaks. We can't have 1.7 leaks. They occur singular. So we have 1 leak, we have 2 leaks, we have 3 leaks, and so on. So 1 minus the probability of x being less than 2 is the same as 1 minus the probability of x being less than or equal to 1. Because keep in mind, if we are dealing with a discrete count of things, 1, 2, 3, 4, 5, being less than 2 is the same as being less than or equal to 1. And on our GDC, that's how we can calculate it. The cumulative Poisson distribution function is less than or equal to. And so really easy to miss that. And because we have a count of something, it does make a noticeable difference. And so again, this part here is easy to do on any calculator, but the hard part is getting to that. And so this here is what I really want to type into my GDC. And so again, we'd be using the Poisson cumulative distribution function with the mean still of 3, where x is less than or equal to 1, or 1 minus all of that. And so if you type this in, you get something like approximately 0.801, so pretty much 80% probability there'll be at least 2 leaks. Keep in mind, if you didn't take this into account and you just found 1 minus, you had x equals 2, you get a distinctly different answer. So really got to be careful with that, because again, as it says up here, a Poisson distribution, the events always occur singularly, one at a time. So we have a count of them, and that'll come up several times. All right, so here we have a different one. We have a railway in which the flaws of the tracks follow a Poisson distribution. Okay, so we know on the left side of the track, due to how they're installed, there are on the right side of the track, there are 5 flaws per kilometer on the right rail and 2 flaws per kilometer on the left rail. All right, so let me just kind of get some of these things written down here. So on the left rail, I'll put the right rail, MR, there's 5 flaws per kilometer. On the left rail, there's just 2 flaws per kilometer. So if we look at the question, though, we want to start paying attention to planning for a 20-kilometer track. So I want to take these averages and I want to scale them up. So I want to think in terms of flaws in 20 kilometers. So I just need to multiply each of these by 20. Drop my pencil. Times 20 times 20. So I can say now this is the same as 100 flaws per 20 kilometers on the right side of the track. And this is 40 flaws per 20 kilometers. So if I add these up in total, we have 140 flaws per 20 kilometers on average. And the reason I want to use this is for my M, I want to think in the number of flaws per 20 kilometers is because that's the scale we're having here. And with Poisson distributions in general, whatever your average rate is, we can scale it up or down for what the question wants us to take into account. So for this, though, we want to find what is it says the company wants to budget enough money, so there is a 95% probability that they will be able to repair all the flaws in the new track. How many flaws should the company budget for? Basically, how many flaws will bring us to as close as possible to a 95% probability of that occurring. So a more formal way of writing this, we know our M value, it's 140 per 20 kilometers. I'm trying to find, knowing it's a Poisson distribution, what's the probability that X is less than some number, I'll call it K, and we want that probability to be more than 0.95. So what is the least, what was it here? Sorry, I want to make sure I have this written down right. There is at least a 95% probability. So at least 95% means greater than or equal to 95%. So that's it. In this case, I don't know what the K is. And while I could do trial and error, I know the average is 140. That is quite time consuming. But we can use our graphing device, and we can either graph or probably use a table. And I would just go to Y1 in your graphing screen and type in a Poisson cumulative distribution function in which the average is 140, and just leave X as X. And that will be graphing me. Keep in mind, that will be graphing where we have, that's graphing this, where X is less than or equal to this. That's it. If you try to actually graph it, you'll find it's really, really slow. A table's a little bit better, and you can adjust your table settings, and you should quickly find that we get when X is at 160. So 160 flaws. That's the first time it breaks 95%. Everything less than 160 flaws is under 95%, and we want greater than or equal to 95%. And so in this case, we want to budget for 160 flaws. I don't have the exact numbers on my written down here, but when you look at your table, and again, I think the table is much easier to work with, when you see 159, it's just shy of 95%, and 161's above it. So 160 is what we should budget for here. And in general, you'll find when we have questions like this where we know the probability but we don't know the number, your table feature is probably a lot more helpful than the graph. The graph can be really slow, especially on an older TI-84. It can take upwards of a minute just to make a graph, which is a poor use of time. Or the table can be much faster. So we definitely want to be familiar with how to use our table here. Lastly, tough question. We have an advertising agency. They want to, I don't feel like reading all this. The key is you can read it yourself. We have 2 billboards. One billboard is by a road that gets an average of 1,158 cars per hour. And the other billboard is by a road that has an average of 1,650 cars per hour. And the number of cars passing each billboard follows a Poisson distribution. We want to find the largest possible value for X, for which the advertising agency can claim accurately that together no less than X cars pass the 2 billboards per minute for at least 95% of the time. Okay, a lot of stuff to unpack here. First, the key is we want to think per minute. So I want to scale down these averages. And so, for example, this first billboard. Instead of 1,158 cars per hour, I'm going to divide by 60 and get 19.3 cars per minute. And for the second billboard, instead of the 1,650 per hour, divide by 60, and I get 27.5 cars per minute. So at least we have these scaled down to the time frame asked for in the question. So put these together, and we can see our average. So M or mu, whatever you want to use, together is 46.8 cars per minute. That's the average rate of cars at these 2 billboards together. All right, so we want to find the probability for where it's at least 95%. What's the lowest number, the largest number, for X, or the largest number of cars we can claim accurately will pass, at least 95% of the time. And so to make this a bit more formal, we're trying to find the probability where X is greater than or equal to some number. Again, we don't know it. And we want this to be more than or equal to 0.95. Like before, we don't know what that K is. But I do know the average. And I know I want it to be more than 95%. Remember, again, our calculators aren't so good at telling us more. So I'm going to adjust this and write it as all those lots of approaches. This is the same as finding the probability that X is less than K, less than 5% of the time. So these two are equivalent. Finding where it's more than or equal to, where that's more than or equal to 95% is equivalent to finding where it's less than that 0.5% of the time. 5% of the time, 0.05. So with that said, I again want to use my GDC. And again, I'm going to go to my equation editor, but I'm going to use a table. And I want to type in the Poisson cumulative distribution function with a mean of 46.8 and the X value of X. That said, we look at our table. And when X, if I look at kind of an example of my table here, actually, I'll just write it like this. When we see X is at 35, when on my table, that means when the probability of X being less than or equal to 35, that's what the calculator's figuring out. When we see 35 on our table, it says there's a 0.0445 probability. And the very next line, when X, it says, is 36, which means a probability of X being less than or equal to 36. That the calculator says 0.0616. So got to be careful again, because really we're trying to solve this right here, which is just where is it less than K, not less than or equal to. And remember that K, or this 35, this 36, this represents the number of cars passing by. There can be 35 cars passing by in a minute, there can be 36, but there can't be anything in between that. So this first, what seems like the solution of 35, because I have a probability just shy of 5%. Keep in mind that's the same as the probability of X being less than 36. being less than or equal to 35 is the same as being less than 36 when we're dealing with whole values. It's kind of like the first question we saw today. And if we look at what we have here compared to what we're trying to figure out, this doesn't work. When I have a 36 right here, the number I have is a little bit too small still. Oh, sorry, what am I talking about? It's correct. Oh, I screwed up. This is where I should re-edit the video, but instead I'm gonna go clear my throat and maybe erase this and just say, hey, why don't you ignore the last minute of the video? And you can curse and complain about me all you want. Keep in mind, these videos are free. And I'll just go back to what I had right here. So, and again, everything here was correct. I just started screwing myself up at one point here. And so just keep in mind right here, this value here of x equals less than or equal to 35 is the same as where the probability of x being just less than 36, which is actually means that that's the answer we want, 36. Because if I look at the next one, that's the same as x being less than 37, right? Less than or equal to 36 is the same as x being less than 37 when we're dealing with whole values. That probability now is too big. And so this here is what we want to look at. But just keep in mind, again, it's easy to think that 35 should be the answer. But again, we want to find where it's less than that number, not less than or equal to. So 36 is the answer we need to have here. And so in the end, x equals 36. Confused? Well, I can't blame you. I screwed up how I was explaining that at the end. But in its essence, everything I'm talking about at the end here is the same idea as what we saw right here. If we're trying to find where something is less than a number with a distribution like this, then keep in mind, if we're using that cumulative distribution function, being less than 2 is the same as being less than or equal to 1. And if I look back right here again, everything I'm doing in my calculator is less than or equal to. And so if I want just less than, I have to think, okay, less than or equal to 35 is the same as being just less than 36. I hope you accept my apology, but I'm done.